In this video, we'll learn about object-oriented programming as a concept. When a car is manufactured, it is built by assembling thousands of components that work together to deliver the core feature set, the ability to drive the vehicle. These components are themselves made up of several components. For instance, the engine is a complicated machine made up of thousands of well-engineered components. Likewise, the transmission, suspension, the brake assembly, the electrical system, everything is a self-contained component that contributes its set of functionalities towards the larger goal of working with other components in the car. Every component exposes an interface which enables it to be connected to other components easily without worrying about how that component works internally. In fact, every product is manufactured in the same way. For instance, in your mobile phone, the camera is a self-contained unit with all necessary optic and electronic components, and it just plugs into your phone's main circuitry. Likewise, the display unit or the screen is a self-contained unit as well. These components are often manufactured by multiple companies and are assembled, and they work because there is an agreement on the interface through which components would talk to each other. Things are quite similar in the world of software development. When building a large application, you'd often deal with a lot of diverse functionality, each of which is made up of its own set of variables, functions, and other code. These pieces must work with other pieces as you put together the application. This is where object-oriented programming helps us. It is essentially a programming model, a set of concepts, which, when implemented, enables us to systematically build large and complex applications with well-defined and organized components, data, and interfaces. Let's begin with the most fundamental piece in object-oriented programming, the object. An object is a collection of variables and functions that are related and form part of a single entity. This grouping brings several advantages that we'll explore in the video. To understand this better, let's say you're building a large application like Prism that you're using right now, which must handle thousands of users in various roles and functions such as learners, instructors, mentors, learning advisors, and so on. Each user, depending on the role, might be able to do things specific to their role. For instance, you're a learner and you have access to your learning dashboard and the content. But underneath all of this, a user is an entity with some basic attributes that are common to everyone, irrespective of their role. For instance, every user has a name, an email ID that works as the username, and a password, and an optional profile picture. A user might also have other properties like age, location, a contact phone number, and postal address. So a user such as Diego Marcus here is like an object because the user has a set of basic properties associated with him, and this user might also have some basic built-in functions too. For instance, a function to change the user's password, update the postal address, location, contact number, and other properties. By putting these elements together, the user becomes an actor in the grand scheme of your application design. While Diego Marcus here is an object, it would be created as an instance of a template that we must define. So in this case, Diego Marcus is made from a template known as user, which defines the base variables and properties that Diego will possess when this specific user is created. Think of it as the mold which is used to create an object. In object-oriented terminology, these molds are known as classes. A class is a structure that contains the variables and functions, which I'll now term as properties and methods to be precise, that are related and describe the internal data and functionality of the instances that will be created from the class. Every time a user signs up, they will be created as instances of the user class and will get all the properties and methods that you've defined in the class. So when Janet Howard joins Prism, she too would have all the properties and methods that Diego Marcus has. At the foundation level, classes help group related properties and methods into templates with which objects can be instantiated. For instance, on an e-commerce site, there may be hundreds of kinds of products such as books, electronic gadgets, and more. But at the fundamental level, all items could spawn from a base template, a base class called product. This class could include properties such as the name of the product, the cost, quantity in stock, along with methods to change the price if needed and change the quantity. Every product that gets into the system would then be an instance of the product class and would have the associated properties and methods. Now that you understand the concept of a class, let's look at the 4 key principles of object-oriented programming that will help you understand this software development model better. The first of these 4 principles are called encapsulation. In simple words, encapsulation means that data can be kept privately inside the class structure without letting the outside world access it directly. This enables us to prevent any unwanted changes or modification to data by code outside of the class. Essentially, you want to hide away the inner workings of the class from the outside world. With encapsulation, we include methods in the class which have access to this data, and these can be exposed to the outer world to allow reading and writing data to the private properties in the class. Why do we do this? Well, it gives the advantage of knowing precisely how our data in the class is getting modified or read for use. You get control. To the outside world, there are 2 kinds of methods that they can use. The getter methods are used, as their name implies, to read data from within the class. Think of checking your account balance at an ATM machine. You press a button and it displays the balance in your account, but doesn't tell you how it is accessing this data or where this data is stored in the system. In the same way, getter methods will provide you access to the data for reading purposes. When you have to modify data in a class, you can use setter methods, which are designed to safely modify data in the class. And this also means that you can thoroughly validate the changes being requested before you implement them and can also keep track of the changes. So once again, control. So in terms of our ATM analogy, when you withdraw cash, it causes a change to your account balance, but all of that is done internally without exposing the specifics. To you, the only action allowed was withdraw. Well-designed setter methods can ensure that no untoward changes are made to data that should stay private. Our second principle is abstraction, which will sound very familiar to encapsulation because it builds on top of it. Abstraction refers to the methods that a class exposes to let the rest of the program operate on its data and features. If you look at our ATM machine, it provides a fixed set of options and features for users to interact with their bank accounts. The user is only expected to be able to work with these limited features, and the user is not expected to know the inner workings of the ATM machine or how these features work on the inside. When a class is created, it should be designed in such a way that the users of the class should only be concerned with the methods and the interface that you expose. Those act as controls with which the outside world can interact and use the class. The third principle in object-oriented programming is inheritance. One of the superpowers that you get with object-oriented programming is the ability to create classes that build on top of existing classes by extending their features. This is incredibly powerful because you can begin from a base class and create multiple classes that each share the base set of capabilities from the parent. So our user class might be extended to create the learner and instructor classes. In this case, the learner class might get controls to view study material and access online classes, whereas the instructor gets controls to start an online class, share resources with students, and view grades of all students in the class. In object-oriented parlance, the user class here would be termed as the superclass, as it is the parent from which the learner and instructor classes have been extended. The learner and instructor classes would be known as subclasses, and they can not only access properties and methods from the superclass, but can also override and modify them to suit specific needs. Likewise, a book class might hold the title, author, ISBN number, publishing date, and category, but it can then be extended to a magazine class with subscription related details, publishing frequency, and other magazine specific data and features. Inheritance allows us to create variations of a base class and iteratively build your application's capabilities. The fourth and the final principle is polymorphism. This principle simply refers to the ability of subclasses to override methods from the superclass and is something we just discussed. With polymorphism, you can have the same method name in the superclass and the subclass, but with completely different implementations. This allows us to fine-tune implementation of methods based on the specifics of the subclasses while maintaining the same interface. This specific flavor of polymorphism is also known as dynamic polymorphism. With these four principles in place, object-oriented programming offers several advantages. By organizing code and data into classes which can instantiate objects, you can understand the inner workings and identify the source of errors and problems easily. This modularity is very helpful when working with large code bases. Object-oriented programming also ensures that you reuse code, and with polymorphism, you can easily extend capabilities and bring about dynamism within the structure that comes with the architecture.